Okay, so here's where we were last time. We were talking about surface independence. Right? Let me just remind you, surface independence is just like path independence. The same idea, just shifted over one sort of one dimension on the diagram, if you want to say it that way, one notch further to the right. So the summary then is that a vector field is surface independent. By the way, again, important reminder, assuming all functions and vector fields in discussion here have all the regularity necessary, things do change if we have singularities of given sorts, and it's a problem. And anyway, so assuming everything is fine, surface independent means it's a curl of something. And furthermore, it means that the divergence is zero, and vice versa. So all three of these conditions are simultaneous. Again, just like with path independence, what's amazing about this is that on their faces, all three of these conditions look totally different. Right? So this is a statement about your vector field being a derivative of something. This is a statement about your vector field's derivatives itself. And this is a statement about integrals of your vector field. Okay, so it's quite remarkable that these are all simultaneous as they are. Okay, so example, before we're wrapping up this section pretty quickly, by the way. So example, this is pretty much the previous example. You'll notice right away, this is the exact same vector field that we saw in this previous example back here with this surface. And let's see, where was it? Here we go. That vector field, and we have a surface that's the part of this equation, the part that's above the xy plane. So it's pretty much the same example. The difference is, there's that equation above the xy plane. The difference is that here, I'm no longer going to tell you this free information that your vector field is a curl of something. Not going to give you that free information anymore. Now that was our foot in the door in this past example here. Our foot in the door was, hey, we're given that it's a curl. Being a curl, that means that it's surface independent, and then I can go on and change the surface, and it's all over at that point. Okay. So here we don't have that foot in the door given, and the only difference then is that we have to we have to figure that out for ourselves. You're going to have to demonstrate that this is surface independent. No freebie anti-curl being given. Notice that the way to get the surface independence that I need is simply take the divergence of the vector field that you want to conclude is surface independent. Make sure you get zero. If the divergence is zero, your vector field is surface independent, and then everything proceeds just as it did before. So that's all you got to do here. Take this vector field, compute its divergence, note you get zero, and everything else is just like before. Okay. All right. So a last comment about surface independence. It's like I say, it's really just like path independence on the diagram, right? I mean, you look at this diagram here, and surface independence says two surfaces that have the same boundary curve, the value of the corresponding fluxes must be the same. Path independence says two curves that have the same boundary points, their line integrals must be the same. I mean, it's really, really analogous, right? So I'm going to make the claim here, though, that surface independence as a computational tool is more useful than path independence. And here's why. Let's talk about path independence for a second. How can we use path independence? Path independence, well, only if the vector field is path independent, which would mean that its curl is zero, which would mean that it's a gradient of something. And here's the thing. If it's a gradient of something, we already have a great tool. If you have a vector field that is a gradient of something, most of the time, as a computational tool, when it comes down to plugging and chugging, compute the anti-gradient and plug in, right? So the situation with path independence is, I like analogies, right? Path independence is like a really great high-quality screwdriver, but you already own a really nice high-quality screwdriver. So yeah, it's useful, I guess, right? But I mean, it gives us capabilities we already had. So it gets a little philosophical. How useful is that? Anyway, now of course, I also made the case that computational ability is not the only point to path independence. Path independence as a concept, as a tool for connecting ideas with other ideas. Extremely important, right? This idea of potential energy, the idea of conservation of energy, extremely powerful physics, mechanics, computational tool comes about. It is created by this concept of path independence. So I'm not saying path independence is useless. Oh no, it's very, very useful. But when it comes to plug-in and chug-in, we kind of don't really need it. Surface independence, on the other hand, let's try to apply the same argument. Go down here to the diagram. Well, if a vector field is surface independent, right, then that means we already know it must be a curl of some other vector field. Phooey on surface independence. How come I don't just use Stokes' theorem and rewrite my flux that I'm trying to compute as a line integral? Why don't we just do that? And the answer here, something we haven't really talked about yet, but this process of finding an anti-curl is hard. You may have noticed I never brought that up. All right, we talked about how to find antigradients. Never noted how do you find anti-curls. And we're not going to. It's a hard thing. It's not really something we can do in this class. Right? So, path independence is a screwdriver where we already own a screwdriver. Surface independence is a hammer. We did not previously own a hammer. That makes it really valuable. Everybody see what I'm talking about here? I mean, in this situation, this ability to change from one surface that I don't like to a different surface that I do like, I'm out of other options. So that makes it very useful as a computational tool. Okay, all right, enough of that. Okay. So moving along, next section here, we're going to talk about a kind of a silly metaphor that I've created. I don't know, I think I created it. It's possible. It almost certainly have been out there in the past, but I like this little silly metaphor I'm about to show you. Let me remind you though of the context. Here are our diagrams. And we came up with a bunch of context, and we motivated the gradient operator in the process of thinking about the fundamental theorem of line integrals. Then we motivated Green's operator, thinking about Green's theorem. We have likewise a three-dimensional diagram, and we have these operators that have come about one at a time by thinking about these boundary theorems, accumulation theorems, whatever you want to call them. Okay, what we've seen is that this story here is highly analogous to this story here, which is highly analogous to this story here. So there's strong analogies between how these operators behave in their appropriately different circumstances. Okay, that's true. Now here's another thing, and this is another selling point for the diagram. It's not just about analogies. There are connections between the operators themselves, composing them as indicated in the diagram, taking the curl of the gradient of a function, taking the divergence of the curl of a vector field, composing these diagrams like this. Really interesting things happen. So that's what this section's about. I want to talk about these, the way these operators interact with each other. This is what I'm going to introduce with a metaphor. Again, this is a silly metaphor. I'm going to create something called a life cycle of an integrand. Again, it's silly. I'm not going to say this many more times, but I just want to emphasize, this is silly. Don't take this too seriously, right? Nothing that we're about to discuss is actually alive, right? But I think the metaphor is really convenient and really nice. So I want to look at our diagram and think of this process of applying operators. Note that increases the dimension of the context by 1. Every time you apply one of these operators, the the dimension of your context goes up by 1. And I want to instead think of this as an indicator of time. It's a metaphor. It's not actually time, right? But in my little metaphor, I'm going to think of this as being time. Okay. So the act of taking the curl of a vector field. Well, we were at time equals 1, and after taking the curl, we're going to think of that as being time equals 2. And I'm going to think of this as this thing, which exists, and work with me here. I'm going to say that it's alive because it exists. That in this action of applying curl, and time passes, and if I get something that's alive over here, then it has survived to this next moment in time. It's just a metaphor. Please, again, don't take it too seriously. Okay. All right. So we're going to be talking about the passage of time. We've talked about alive. Alive means it's non-zero. Survived means that it's still non-zero after you apply the operator. Okay. Now, on the other hand, what would happen? What would be our metaphor if I had some vector field, alive, non-equal to 0, if I took the curl and if I got 0? 0. Well, that's nothingness. If I take the divergence of that 0, of course I still get 0. I get more nothingness. I get an unchanging, interminable nothingness. I'm going to call that death. It's just a metaphor. So, don't take it too seriously, right? I know it's silly, okay? But I'm going to think of 0 as being death and non-zero as being life. All right? Okay. All right. Now, here's another part of the metaphor I want to talk about. Let's suppose I have something that's alive here, and let's suppose that I apply the operator, and let's suppose that it's alive here. What if I ask the question, well, yeah, but is this right here a survival? Is there some thing over here that survived to this? Or perhaps is this the first time that this shows up? And there's just nothing has survived to become this thing. It's just, this thing is just here on its own for the first time. And I'm going to call that birth. Again, with the metaphor, right? But if it did not have a previous existence before this, then that's its first time to be alive. I'm calling that birth. Okay, so that's our sort of life cycle. We've got a notion of a birth. We've got a notion of survival. We've got a notion of death. We've got a notion of time. Silly metaphor. Again, don't take it too seriously. Okay. All right, so a couple of examples. Let's look at this function right here. That's a function that I want to think of as being in column 0, just because. My example, right? Okay, so that being in column 0, let's apply the gradient operator. That gives us a vector field there. You'll notice that it is still non-zero. So what we have is a survival. This blue function in column 0 has survived to become this purple vector field in column 1. Just for example. Okay. Right, well, then I can apply the curl operator. Take the curl, well, look at this, I get 0. And so it has not survived to column 2. It has a death in column 2. So we have a birth, we have a survival, we have a death. And by the way, I say that this is a birth because there is no previous, there's nothing over here. There is no, could not have come from a previous column. There are no previous columns. And you might say no fair, but that's the way the analogy breaks down. Okay. Likewise, there's nothing over here. There's no after 3. I don't know what you want to call that in the metaphor. The universe ends or something, right? But there is no time after column 3. Okay, so birth, survival, death. How are we doing? Is everybody on board? Okay. All right. Here's another example. Suppose I were to think of this vector field here in column 1. And, well, I could apply the curl operator as the diagram tells me to. The curl gives me this non-zero thing. And then I could, after that, I could take the divergence I get 0. And so death. So another birth, survival, death. Okay. I say birth here because there can't be a previous thing that survives to this. There is nothing whose gradient is that vector field. Now, how do I know? I know because path independence, right? If this were a gradient, then the curl would have to be 0, but it isn't. Okay. All right. So birth, survival, death. All right. So with this metaphor constructed, let me show you why I like the metaphor. There's a really nice little summary of a large number of theorems that all get compactified into a single statement in the context of this metaphor. And the statement is, every integrand has a lifetime of 2. 2 is a magic number. Everything is a lifetime of 2. Asterisk. There is a single exception. I'll talk about that in a couple minutes. It's a kind of a trivial little exception. Trivial and obvious, and it's just a formality that has to get said. But other than the single exception, every integrand has a lifetime of 2. Now, what does that this tells you a lot of things. Here are 8 separate theorems that I claim are really just that statement applied to their context. If you want to think of and learn 8 separate theorems, I suppose you can, right? And, that's not crazy, right? But it's so much more convenient and compact to just remember this little rule. Every integrand has a lifetime of 2. Okay, so for example, let's look at one of these. Let's see here. If Green's operator is 0, then it's a gradient of some function. Now let's look at that on the diagram. Now that's a theorem, and again, you can think of this as a theorem stated as it is. If Green's operator is 0, it is a gradient of something. Okay, so to our diagrams. We're on the R3 diagram here. Let's go up to the R2 diagram where we have Green's operator. Statement that we're looking at. If Green's operator is 0, it's a gradient. Okay, if Green's operator is 0, then there is an anti-gradient. In other words, our vector field is a gradient of something. This thing is a gradient of something. So now let's look at this this assertion. Well, if it dies here, right? That's what Green's operator equals 0 means in the context of the metaphor. If it dies there, it's saying, this result is saying that it is born here. Well, again, that's just a lifetime of 2. All this is saying is, well, if it died here, then given its lifetime of 2, it must have been born here. In other words, this vector field that we're looking at must be a survival from column 0. Yep.
Does it have to be like a closed boundary for us to calculate Green's operator?
I don't know what you mean by a closed boundary. So these are just, we're just talking about functions in vector fields. We're not talking about curves and surfaces and stuff like that. Okay. So that's just the operators and the integrands is all we're talking about. Okay. Yep. Does that make sense? I mean, yeah.
I think so.
Okay. Yeah. Okay. So in other words, now why would we be interested in talking about these things? Well, it's because they're going to be part of integrals. And integrals do have domains, and yes, absolutely. But what we're doing right now is looking at, just integrands and how we will use this information in integrals. We'll get to that later. Yeah. Okay, so likewise everywhere else, right? If the curl is 0, then there must be an anti-gradient. Now again, this is something we already knew. We knew this from path independence, but notice it fits this pattern of death here. Therefore, birth here. Okay. All right. So I have these summarized in the form of this notation down here at the bottom. You'll notice I've appended my diagrams to have a little bit more on it. These are just little compact notations for these results. In this notation, solid lines are the hypothesis part of the statement, and then these dotted lines are the conclusions. So this statement right here says, if you have a vector field that is a gradient of some function, then that function, then that vector field, if you apply Green's operator, you will get 0. So this is the if and this is the then, if you will. Okay. All right. So if you have a gradient, Green's operator is 0. If Green's operator is 0, then there is an anti-gradient. That's what these two compact notations say. And then likewise over here, we have these notations down here like this. If you're looking at a gradient, the curl is 0. If the curl is 0, you got yourself a gradient, etc. Again, assuming regularity, assuming everything in sight is appropriately continuous and differentiable and all that stuff. If the divergence is 0, then you have yourself a curl of something. Okay. All right. So again, there's a bunch of these theorems, and I encourage you to think of them not individually as separate, unrelated facts. Think of them as all being really morally the same fact. These are all the same statement, just applied in different contexts. If you look at them individually, that statement there and this statement here, they look completely different, right? But they're all just in different contexts. This same statement. Okay. So that's most of the content of this section of the book, the lifetime theorems. All of the lifetime theorems are really just this. Now, some details that I have to talk about. First of all, let's talk about that exception. The exception is constant functions in column 0, and it's an easy exception to notice. If you have a function here that is constant, right? You take its gradient, you get 0. And it's a sad little story of a life taken too early, right? But that's the exception. That's the one exception. Constants whose gradients, of course, must be 0 do not have a lifetime of 2. They have a lifetime of 1. Yeah? Everybody see what I'm talking about? Okay. All right. Okay. Yeah. Okay. So again, very, very important. Everything's got to be defined and continuous and differentiable, even if there is so much as a single point, right? So if there is a single point where, well, my vector field's not defined at that one point, all bets are off. Okay. All right. And there's an exercise that elaborates on this in detail, and I have to admit I can't remember off the top of my head if that's assigned or not assigned. But if you're curious about how important is it, that we not have singularities, even so much as at a single point, then this exercise here is a good exploration that'll show you what can go catastrophically wrong if you remove this condition. Okay. All right, so let's do an example. Here we go. Let's look at this vector field right here. There's a vector field, and I want to compute a line integral of that vector field. Now, how am I going to compute a line integral of that vector field? Well, we've got options. Line integrals I could parameterize and plug and chug. That's an option, right? But what we'd really like to do, our greedy option, our lazy option would be, wouldn't it be nice if we could use the fundamental theorem of line integrals? Then I wouldn't have to parameterize, and I wouldn't have to do any resulting t integrals, and wouldn't that be nice? Let's consider the possibility that maybe we can use the fundamental theorem of line integrals. So I could just try to compute the antigradient, right? And you could, well, that's fine. But let's try to figure out in advance whether this is a wild goose chase or whether it's something that's going to actually have potential of working. In other words, is there an anti-gradient at all? Right? Don't go looking for something that we know for sure doesn't exist. Right? So let's see, is there an anti-gradient before we get into the work there? So we take the vector field that we were given, compute the curl. It's not zero. Game over. There is no anti-gradient. You don't have to play a game that you might inadvertently cheat on, accidentally do a little fake algebra and find a false anti-gradient that doesn't actually exist. Right? There is no way to win the game. The curl isn't zero. So going back to our diagrams, we had a vector field here. We took the curl. It's not zero. So let me diagram this a different way. Our vector field that we're interested in, it was alive there, and it's alive here. It can't also be alive there. That would give it a lifetime of at least 3, and that's not possible. Right? So simply by virtue of the fact that the curl is non-zero, I know 100% for sure there is no anti-gradient. Everybody on board? So since I know it doesn't exist, I'm not going to try to find it. Right? Don't try to find an anti-gradient for that vector field. Okay, now let me note, in fact, what this example that I've shown you, it's actually even easier than this. Okay, so I did go ahead and compute out the whole curl here. Right, there's the curl, and it's got components 1, 2, and 3 there. And as I was computing, notice as soon as I compute component 1 and see that that's not 0, I don't even have to compute the rest of the components. Who cares about what the rest of this is? Even not knowing that, the mere fact that the first component is not 0, that tells me that the curl is definitely not 0. I mean, I don't know what it is exactly, but it's definitely not 0. So even after looking at that one component, you're done. Everybody on board? In fact, it's a little easier than that even. Let's come over here and see how this calculation goes down and how do we compute curls. Zoom in here. The way we compute curls. Well, we have this formula for curl, and you do it by, it's del cross. Right? How do we do cross products? Well, we do cross products with, little fake determinants. Right? So the nice punchline then is I can write that as partial with respect to x, partial with respect to y, partial with respect to z, E1, E2, E3. I can just write the matrix I can sort of, conveniently take advantage of the fact that my vector field is written horizontally, and just there's my matrix that I need to take a fake determinant of, right? And so let's compute that determinant. And well, let's see, the first component of the determinant is going to come from taking the y partial of that and then subtracting the z partial of that. And notice this little calculation is really, really easy, and I don't even need to write down most of what I wrote down. I can remember that I'm doing the determinant thing, and that I'm doing this whole, sort of cross, sub-matrices thing. And I can just remember that these partial operators are which ones are where. So without even writing anything down, in your head you can say, look, that first component's going to be the y partial of that. That's clearly z. Minus the z partial of that, which is clearly x squared. You've got z minus x squared. You didn't even have to write anything down. Right? It's really easy. In your head, boom, that's not 0, game over. There is no anti-gradient. Right? So there's been a couple of instances in the past few lectures where a vector field has come up, and I've made the assertion that oh, by the way, I know that there is no anti-gradient, so let's use Stokes' theorem, or let's use path independence, or whatever. And this is the little trick that I pulled. It's not a hard trick; it's an easy trick. And you compute any one of these components. Any one of these components. If you get not 0, game over. Okay. Now, if you get 0, You got to keep going, right? Simply knowing that one component is 0 is not good enough. The other components could be non-zero. But if you get non-zero, game over. Okay, so anyway, that's a nice trick. Okay, there's some other examples here. I guess I'll do this one real quick. Suppose we want to compute a flux of that vector field going to the diagram. I'm computing a flux, therefore the vector field is here. Let's ask the question, is there an anti-curl? Now, side note, we don't know how to compute anti-curls, right? But if just for whatever reason, if I just want to know if there is one, does there exist an anti-curl? All I have to do is compute the divergence, and if I get 0, then there is an anti-curl. And if I don't get 0, then there is no anti-curl. Okay. And let's compute this divergence. Here it's an easy divergence to compute, as it turns out. Keep in mind, first component, second component, third component. We're going to take the x partial of that. Well, there's no x's. We're taking an x partial of an expression with no x's, so the first term is clearly 0. And then, here, let me color code better. The second component, I'm going to take the y partial of that. Well, there's no y's in there, so that second term is going to be 0. And then I need to take the, for the third component, I need to take the z partial. Well, there's no z's in that third component, and so that third term is going to be 0. So not only is the divergence 0, it's what I'm going to call obviously 0 because it's the sum of 3 zeros, all of which are 0 for pretty clear reasons, right? The mere fact that there's no x's in here, no y's in here, and no z's in here, I can, again, at a glance, now you won't always get this lucky, usually you won't get this lucky, right? But nevertheless, it's a good little thing to be on the lookout for. You never know when you might get lucky, right? And and when it happens, again, it's pretty sweet. So easily seen that the divergence is 0. Okay. All right, there's a few more examples I'm going to let y'all read. I want to get to the physics on this. There's a little bit of physics that relates to this, and this is worth talking about. You may recall we talked about Maxwell's laws, and one of them says that the curl of the electric field is 0. Now this is a steady state. This means nothing's changing, so specifically the magnetic field is not changing, so you can't have this, this is not an electric generator type of situation where the magnetic field is changing. Okay. So in that steady state situation, Maxwell's law says curl is 0. And let's just think through what are the consequences of curl being 0? And if we think about this from the point of view of lifetime theorems, well, if the curl is 0, that means that our electric field, whose curl is 0? Our electric field is a gradient of something, and that something is a function, has to exist, right? And this is a function that is really important in physics. This anti-gradient function of the electric field, that's called electric potential. And there's an awkwardness with a minus sign, unfortunately, and this is just weird, but electric fields point away from higher potentials. Electric fields point away from positive charges. Gradients are supposed to point toward positive charges. So this is fixed with a minus sign. Don't sweat it. It's just it's detail, right? So that's what this minus sign is in here, and let's not worry about that. But so this is the potential function. I mean, again, in a math class, I would call it the anti-gradient, but in a physics class, they call it the potential function because it represents potential energy. As follows, let's write down what Stokes's what the fundamental theorem of line integrals says about this statement here. Line integrals of the electric field, right, equals f of b minus f of a, so potential at b minus potential at a. And so you can see right here how this represents potential energy. This function here, by virtue of its values, is telling you literally this line integral of an electric field. It's telling you work. That's what a line integral is. A line integral of an electric field says you're moving with a charged particle through an electric field. Therefore, you're exerting forces and expending energy. How much total energy is kept track of by the potential energy function. Okay, so the common terminology, the units to describe this is voltage. Let's see, where did I write that down? I guess I didn't. Did I not write that down somewhere? Anyway, we use V because the units are voltage. Now, if you ever wonder what volts are, that's what volts are. Volts are the units of potential energy. It's the units of the anti-gradient of the electric field. All right. Now, I think a lot of y'all have seen a version of this somewhere before. I think a lot of y'all have probably at least heard of electric potential energy at least. A lot of y'all have heard of volts. Right? In fact, anyone who's been careful while changing a light bulb has probably seen volts. Okay. There's another version of this. What we've seen here, that Maxwell's laws, by virtue of implying an anti-something, create a physical concept, a physics concept. It just happens one notch over to the right, and here it is. Here's another one of Maxwell's laws. The divergence of a magnetic field is always zero. Now that's just a different one of Maxwell's laws. That's one of the four. It's on the list somewhere. It was back in the section on divergence. Okay. Well, notice again, this is saying that an operator gives you zero. This is telling us about a death. And that tells me for sure 100% then that means that there is a birth 2 steps previous. In other words, this vector field, the magnetic field, has for sure 100% an anti-curl. Right. Excuse me. Now, so let's write down, analogous to what we did here, let's write down the corresponding, what does the boundary theorem say here? In other words, Maxwell's law has a consequence that there exists a certain thing that is involved in a cool theorem. So let's write that down. And a reminder of what Maxwell's equations say. I'm going to have to write it down here where there's more space. But flux through a surface of the magnetic field, dot ds, I'll say of the curl field, flux of the curl field, is a line integral around the boundary of that surface of the anti-curl. Right, and by the way, I'm going to rewrite this thing. That's just magnetic flux. And so we've talked about magnetic flux in the past. Magnetic flux tells us something important. Magnetic flux is the thing that, as it changes, induces an EMF in a boundary curve wire. So this is an interesting quantity. And going back up here to path independence, to the voltage discussion. This, being a computation of something interesting, namely work, tells me that that's what this computes, right? How much change we have in this function is computing for us how much work it takes to move through an electric field. And, well, by analogy then, I can draw an analogous conclusion here. If I'm interested in magnetic flux, I can understand things about magnetic flux simply by looking at circulations, boundary circulations of that thing. So that's what this thing is. We call this the magnetic potential field, because that is a thing that gives us information about magnetic flux. In the same way that this electric potential function is a tool that gives us information about electric line integrals. Magnetic potential fields tell us about magnetic flux. And again, of course, appropriately, right? So if you want to understand magnetic flux, you have to take line integrals of your magnetic potential field to understand those surface magnetic fluxes. Okay. Anyway, one of the things I think is really interesting about this is, here we are. This is a multivariable calculus class. This is a, kind of an intro level math class, and this concept of magnetic potential fields, I never saw it until I was in an upper division physics course. I just think that's kind of interesting and it was, all of my classmates at the time were like, this is mysterious and, what is magnetic potential anyway, right? Well, okay, it's just, one dimension over. Magnetic potential is just analogous to, electric potential and, just interpreted appropriate to the context. So anyway, I think it's kind of interesting. This concept, voltage is all over every light bulb in the world. And everybody's seen voltage. This concept is subtle and exclusive and, abstract and scary. So anyway, the analogy, again, I'm a big fan of analogies. Think about how voltage works. And there's the capability there to capitalize on coming to understand how magnetic potentials work. Okay. Nothing. Okay. A real quick thing I want to say, and I will be really quick about this one. There is a kind of lifetime theorems of sorts, kind of, and again, it's just a metaphor for domains. Right, we've been talking about integrands. And this process of, time sort of passing as you go that way, and created our little metaphor of birth, survival, death, and, lifetime, etc. about integrands. And it turns out, kind of, sort of, if you ask the same question about domains, there's still kind of with some kind of sort of awkward exceptions. There's a lifetime theorems for domains in the process of taking boundaries. So boundaries now are going to be our passage of time. Time now goes that way in our silly little metaphor that I'm creating, because that's how the boundary operator moves. And first observation I'll make is that if you take a boundary of something and then you look at the boundary of it, you never get something. You take a solid. Now I appeal to your geometric intuition. If you take a solid, right, that boundary surface doesn't have an edge, right? Otherwise, Columbus would have sailed off the edge of the earth, right? Right. So, solids, boundary surfaces cannot have boundary curves. And then likewise, going the other way, starting from here, if you have a surface and look at its boundary curve, that boundary curve can't have any endpoints. Right? If you have a fence and the fence stops, it does not enclose anything. You're never going to keep in sheep if the fence ends. The fence has to come back around and close up on itself. It's embedded in the language. Okay. So this mostly goes the other way around as well. If you have a surface that does not have a boundary, let's think that through. If you have a surface, right, and if the surface has a boundary, okay, fine. But if you close up that boundary, if the surface doesn't have a boundary, then it encloses a solid, and therefore that surface is the boundary of a region. Now, I'm just a geometric appeal, right? Then here's the one where there is actually an exception, and I've got to admit that knots are an awkward exception to the next one. But if you have a curve, let's ignore knots for a moment. If you have a curve that does not have boundary points, you have a curve that starts and then ends right back where it started. closed curve. Feels like you should be able to find a surface whose boundary is that curve. And I'm going to say mostly, but again, if you have a knot, you tie a curve up in knots and then end it at the same point. There isn't really a surface as we understand it in this context because of the fact that it's tied in knots. So awkward exceptions. But that said, with that one, I'm going to say kind of rare in our context, rare exception, we have this little nice summary here, and that is that every domain either has a boundary or is a boundary. Right? A closed curve, it doesn't have a boundary, therefore it is a boundary of a surface. A closed surface doesn't have a boundary, it doesn't have an edge, therefore it is a boundary of the solid inside of it. Everybody on board? Okay, so I think this rolls off the tongue very nicely, and it's a nice way to think about it. Okay. All right. Last thing, this is the last section of the book. Now, a reminder, tomorrow we do have to go back to chapter 4 and finish up the stuff that we skipped over. There's a lot of stuff, by the way, in those 3 sections that we skipped over that's pretty supplemental and not necessary, and we're not going to get to it this term, and that's too bad, but it's also not rare. And again, it's supplemental, and it's not essential that we do it. So we're going to make it through all that's important, all that's necessary in those sections. But we're going to finish chapter 6 today. Section 6.9 is mostly just a bunch of examples. We're going to take all the ideas that we've been talking about, and I'm going to show you how to kind of bring it all together, how to turn all these ideas that we've talked about into a sort of an overarching sort of big picture strategy for how to look at a line integral or a surface integral, and how to figure out how do I compute that line integral or how do I compute that surface integral. So how should I proceed if I need to compute one of these things? Okay. All right. So first thing is what I call diagnosis. What kind of a problem is this? Is this a Stokes' theorem problem, or is this a Gauss's theorem problem, or is this a path independence problem, or is this a fundamental theorem problem, or is this a chapter 5 plug and chug problem? Right? How do you know which way that you should go? Okay. And roughly speaking, it all comes down to the diagram. Step 1, figure out where you are in the diagram. So, for example, suppose you're trying to compute a line integral in R3. Okay, hit the pause button right there. Line integral in R3. Come over to our diagrams. Come over to the diagram. Don't look in R2. The question's asking about a line integral in R3, so forget about Green's theorem. Forget about the two-dimensional fundamental theorem. Right? We're not in R2. We're in R3, so we're going to ignore all of that. We wanted to compute a line integral in R3. Well, there's the line integral column. We are apparently in column 1. And notice that this right away gives you some information. Not only are we going to ignore Green's theorem, but fundamental theorem of line integrals is a candidate. Stokes' curl theorem is a candidate. Both of these theorems say something, at least sometimes, about the line integrals that we're interested in. What is not a candidate is the divergence theorem. Right? It's not connected. Doesn't relate to the problem. It's just not going to come up at all. Triple integrals? Right? We were asked to compute a line integral. I might be turning it into a flux. I might be evaluating it with a function, but there's not going to be a triple integral in this problem. Okay, so I just want to let y'all know now, and this happens every term, despite my warnings. So if the question is about a line integral, there should be no triple integrals anywhere on the page. Nowhere on I don't want to see any triple integrals if the question is about a line integral in R3. It just doesn't have any hope or prayer of possibly being relevant. Everybody see what I'm talking about? It looks bad. If the question's about a line integral and you're toying around with triple integrals, it makes it look like you don't have any understanding of what the diagram's telling you. Okay, so now that's just a strategic point, but I think it's an important strategic point. Don't give away that you don't know how to do the question by something like that. Okay, all right. Okay, so you have your candidates. These are the possible theorems. Okay, so the next idea is to notice that you're going to have to, what I'm going to say, go backwards through one of the arrows. So, for example, if you're interested in computing a line integral of this vector field along that curve, let's just say, well, if you're going to use the fundamental theorem of line integrals, you'll need to look at the boundary of that curve. Cool. We know how to find boundaries. If you look at the picture, you can just see what the boundary is. Okay. On the other hand, you're going to also need to find an anti-gradient. Gradient goes that way. I need to go the other way. I need to go backwards through that gradient arrow. I need to find an anti-something. Anti-gradient. Okay. On the other hand, suppose you want to use Stokes' curl theorem. Now again, I'm still computing that same vector field along that same line, same original question, right? To use Stokes' curl theorem, I need to compute curl. No problem, I can compute curl. It's a formula, plug and chug. Computing curl is easy. But I'm going to have to find an anti-boundary surface. Boundary operator goes this way. I need to go the other way and find the thing whose boundary is my curve. And again, we're going backwards through an arrow. And again, there's no guarantee that you can do that. Boundary line goes that way. Going backwards, hey, I don't know if that's possible. So as we were talking about these theorems, in all cases I was describing these as, well, there's an asterisk. There's a catch. It doesn't always apply. So this is just an observation about that. But, if you want to compute a line integral with Stokes' curl theorem, you want to compute that line integral, well, the catch is you can't just do any old line integral. It has to actually be a boundary of something. And you need to know what it's the boundary of, because what it's the boundary of is your new domain. So I'm just rephrasing that now as we have to move backwards through the boundary arrow. Okay. Likewise, if you want to use to compute a line integral, if you want to use the fundamental theorem of line integrals, well, this is not for any old line integral. It has to be a line integral of a gradient. Namely, there has to be an anti-gradient. Namely, you have to move backwards through that gradient arrow. Okay, so all of these theorems, you can see, just look at the ways the arrows are like this, right? And whichever, if you want to use the one on the left or the one on the right, whichever theorem you want to use, you're going to be moving backwards through one of the arrows. So be very clear in your mind. Which cost are you going to be paying? Whichever theorem you're going to be using. Okay. And, make sure to check and make sure that you pay that cost. Okay. So with all this in mind, roughly speaking, here's your strategy. And it's, I think this is a nice summarized strategy. Step one, no matter what kind of an integral you've been asked, line integral, flux integral, R2, R3, whatever, figure out where you are in which diagram. I mean, give yourself the advantage of the roadmap, for crying out loud. All right? So that's step one. Figure out where you are in which diagram. I'm going to say apply the appropriate operator. Let me go back to the diagram for a second here. And let's talk about, I want to compute a line integral. Here's my two candidate theorems. How am I going to decide if I can use the fundamental theorem? Well, I need to decide, is there an anti-gradient? And we have a tool for deciding, is there an anti-gradient? It's called take the curl. Right? So computing the curl will help you decide if you can use the fundamental theorem of line integrals. On the other hand, if you're going to use Stokes' curl theorem, well, guess what? You're going to need to know the curl. Right? So a certain point of view that says if either one of these is going to be useful, either one, you're going to need to know what the curl is in this case. Or in general, now keep in mind, likewise for a flux integral, but either way, you're going to need to know what the operator is that the diagram tells you to compute. And again, I claim the diagram tells you to compute this. If you're asked to compute a line integral over a certain curve of a given vector field, the diagram is telling you right here, oh, you've got a vector field. What do we do to vector fields like this? We take their curls. That's what we do. See what I'm saying? So I'm such a big fan. The diagram is helping you with the question, compute the curl. Now again, in this situation, wanting to compute a line integral, here's another landmine. Dead giveaway. If you don't know how, if you have not the slightest clue what's going on, a dead giveaway is if you take that vector field and compute the divergence of it. It's got no relevance. There's no way that that's going to be useful. Now look at it's not even connected to the thing, right? So make sure not to give me one of these dead giveaways. It really looks bad. Everybody on board? Okay. Likewise, if you've been asked to compute a flux of a vector field, please don't compute the gradient. You can't compute the gradient. Please don't compute the curl of that vector field. This is not over here to which I could then compute the curl. Right? That just doesn't make any sense. If anything, if you wanted to ask, is there an anti-curl? Now that's a good question, right? Take the divergence to answer that question, right? But computing the curl of a vector field whose flux you're interested in, that doesn't make any sense. Right? So again, think of this diagram as a cheat sheet, right? This will tell you how to look good. It will even tell you how, suitably interpreted, how to solve the problem if you pay attention to it the right way. Alrighty. Okay. So you consider your options. If for example, if we're looking at a line integral of a vector field, if you get 0, there's an anti-gradient. You can use the fundamental theorem of line integrals. Okay. If your curve is a boundary, let's suppose it's a boundary of some surface, well, then you can use Stokes' curl theorem. So those are the tools that help you decide which of these boundary theorems, again, if you're looking at a line integral in R3, that's how you can decide which of these candidate theorems applies. And then once you've got your, whichever of these is available, I mean, maybe both, maybe one, maybe the other, maybe none. Right? But once you have your candidates outlined, then you can pick which one of these you think would be the best to do. Right? And don't forget, there is a possibility. It could very well be that the fundamental theorem of line integrals doesn't apply because there is no anti-gradient. Maybe there's no anti-boundary surface because the curve isn't closed, and therefore Stokes' curl theorem doesn't apply. This could happen. This is very real. I had to compute a lot of line integrals in my day where neither one of these theorems applies, and then you just got to go chapter 5 on it and just either parameterize and plug and chug, or hope that you get geometric coincidence, right? Like a dot product that's always 0, something like that, or symmetry, right? Maybe you get lucky with that. Always keep an eye open for those, but again, you may have to actually just take a deep breath and plow through. Okay. All right, so I want to show you a bunch of examples now. We've got some time to go through some diagnoses. Let's start with this one. We're going to compute a line integral. Here's a vector field. There's a curve. It's given by a parameterization. I've got a vector field. I've got a curve. Let's compute a line integral. Step 1, what diagram am I in? Is this an R2 problem or is this an R3 problem? Well, my vector field has 3 components. My parameterization has 3 components. Well, they'd better have the same number of components. Right? So either of these could be taken as the giveaway that we're in the R3 context. This is a curve in R3, a vector field in R3. We're computing a line integral in R3. So here we are in the R3 diagram. We're looking at a line integral. These are our 2 candidate theorems. Please don't write down triple integrals. Don't write down divergence or the divergence theorem. None of that has any chance of possibly being relevant to the problem. Right? So our candidates may be this. Here, I should use a question. Maybe this, maybe this. And let's see, how do we decide? Well, by the way, the diagram tells us to take our vector field and compute the curl. So let's do that. Compute the curl. Turns out you get 0. Now that's algebra. I'm going to let y'all do that algebra. Make sure you can do that, by the way. Make sure you're really good at computing these. I mean, this is all, assumed that that you can compute divergence, you can compute curl, play the game to find anti-gradients, all that computational stuff. Yeah, that's, make sure to drill yourself appropriately and that you can do that well. Okay, so curl is 0. I got 0 there. That means there is an anti-gradient. That means the fundamental theorem of line integrals is an option. And we've got a contender. We could use the fundamental theorem of line integrals on this question. Okay. All right, but don't go ahead and do that, right? Let's slow it down. Consider there's another way to do it. What about the curve? Maybe the curve is a boundary of some surface. Well, you can plug in t equals 0 into there to get the starting point, x of 0. You can plug in t equals 1 to get the ending point, x of 1. And again, now there's some arithmetic there. That's, y'all can do this, plug it in. These 2 points, they're not the same, not a closed curve, and therefore it does not have an anti-boundary. So that's a no on Stokes' theorem. So here's our sort of strategic breakdown, right? We know we're looking at line integrals. This is right out. Fundamental theorem's a candidate. Stokes' curl theorem isn't because there's no anti-boundary. And we pretty much know how to solve this problem now. This is what's left over. Fundamental theorem of line integrals. We're going to find the anti-gradient, plug into the fundamental theorem, and we win. Everybody happy? Again, the point to this example is not to remind you how to use the fundamental theorem of line integrals. The point to this example is to show you how to use the diagram and all the ideas that we've talked about to realize that this is a fundamental theorem of line integrals problem. Yeah? Everybody good? Okay. All right. Okay, let's look at the next one. Let me not get ahead of myself here. So another line integral. I got a vector field, got a parametrized curve. 1, 2, 3 components. 1, 2, 3 components. We're looking at a line integral in R3 again. So here we are again. Line integral. Vector field in R3. This is right out. Okay. What does the diagram tell us to do? The diagram tells us to compute the curl of that given vector field. So let's do that. We compute the curl and we get 0. Now, this is another one of these sort of computational freebies. I like little freebies. I guess there's something naturally lazy about wanting to avoid effort whenever you possibly can, and this is a great opportunity to avoid effort, so let me point it out so y'all can capitalize on that as well. How are we going to compute curl here? Well, there's various rules, and okay, so you're going to take the y partial of that, and you're going to subtract the z partial of that, and then you're going to take the z partial of that and subtract the x partial of that. Notice all these little arrows that I'm drawing here. All the partials that you're going to be taking, they're all diagonal, right? So this first component, you're going to, at some point, you'll be taking a y partial of it, and at some point, you'll be taking a z partial of it. But notice in here, in this function, there's only x's. There are no y's, there are no z's. Likewise, this second component, you're eventually going to be taking x partials or z partials, but this has only y's. Therefore, no x's and no z's. Right? And then lastly, this is all z's. So no x's and no y's. So the fact that this is all x's, comma, all y's, comma, all z's makes this an immediate result. The curl is a bunch of partial derivatives that are all obviously zero. So another thing to be on the lookout for. Now, how often does this happen? Not every time, of course, and maybe not even all that often. But if it does, it's a nice little freak. Okay, curl is zero. So we got zero. There is an anti-gradient. That means fundamental theorem of line integrals is on the table. We've got a good option in front of us. It's nice. What about the other option here? Can I use Stokes' curl theorem? Reasonable question. Well, I need to look at the curve, and I need to ask, is there an anti-boundary surface? How do we decide that? Well, every domain either is a boundary or has a boundary. So we're going to look at this curve and see, does it have a boundary? If it has a boundary, then it can't be a boundary. If it doesn't have a boundary, then it is a boundary of something else. Okay. All right, so we look at our curve. Here's our curve. As before, we take the starting point, plug it in to see where the point starts. We take the ending, plug that in, and sure enough, these 2 points, same point. This curve starts and ends at the same point. There's a remote possibility it might tie itself into knots, but by the way, even if it does, turns out you can still apply Stokes' curl theorem. It still works. It's just harder to actually take advantage of meaningfully. But anyway, we've got a closed curve. So in other words, looking back at the diagram, this curve, the boundary is zero, and therefore it does have an anti-boundary surface. So Stokes' curl theorem is on the table too. All right. So which one's better? Which one should you use? There's a temptation to say fundamental theorem of line integrals because finding anti-gradients is pretty easy. Otherwise, I'm going to be dealing with a flux. Fluxes are hard, right? And, often that's true, but let me show you what's wrong in this case, or potentially wrong anyway. Here's our vector field. Let's contemplate how would we find the anti-gradient here. Well, I'd need to take an x anti-partial of that. Going to take an x anti-partial of that, and that's going to be an annoying integral. Then I'd also need to take a y anti-partial of that. That's not as annoying, but it's still integration by parts. It's right. And then I'm going to have to take a z anti-partial of that, and I don't even know how to do that. Right? In fact, this can't be done in what we call closed form. You've got to invoke Taylor series and stuff to be able to find an z anti-partial of that function. So finding the anti-gradient here is gonna be it's really hard at best, and depending on your constraints, it's kind of impossible. So that's too bad. And all of a sudden, the flux argument started to look a little bit more reasonable. Okay. Some good news happens, though, and it turns out that this calculation ends up being really straightforward. I'm going to show you two different ways to make this argument. One is to say, well, I don't know what this anti-gradient is, but this anti-gradient definitely exists. The fact that the curl is zero tells me that this anti-gradient exists. I don't know how to write it down, but it's there. The fundamental theorem of line integrals tells me that I'm going to compute like this. These 2 points, these are the same point. So yeah, it's f of x of 1 minus f of x of 0, but this is f of a minus f of a. And even though I don't know what f is, f of a minus f of a is definitely 0, and so even though I can't find the anti-gradient, the fundamental theorem approach does still work out really nicely. Everybody see what happened there? This is a neat fact. So sometimes you don't even need to know the anti-gradient to be able to use the anti-gradient. Okay. All right. On the other hand, let's take the Stokes' approach to this. Stokes' theorem says I can write it down like this, and I know that I can apply Stokes' theorem because these 2 points are the same point, and therefore there is an anti-boundary surface. So that's why we know Stokes' curl theorem applies. And the curl is 0. And so check it out. We're doing a flux through an existing surface. We're doing a flux of 0. And so, again, by a very easy argument, we get 0. Yeah? Everybody good? So now, a little trick I want to let y'all know about. Now, this is just strategic observation, but whenever this happens, and this is, I think, pretty easy to persuade yourself, but nevertheless, something you want to think through. If you're looking at a line integral or a flux integral, let me just state it for line integrals. Strategic observation. You can't cite this on an exam, but just so you kind of know and can think, have the advantage on working it out. In any situation where both boundary theorems apply, the answer to the question is 0 because of pick your argument from the others that we just talked about. So that's a neat fact. And now again, you cannot cite, on an exam, you can't say, both of the boundary theorems apply, therefore, per comment in class, this integral must be 0. That's not an acceptable answer on an exam, right? But nevertheless, it's useful to know what the answer is as you're trying to find it, right? So on an exam, you've got to give me one or the other of these. You've either got to make the line integral theorem argument, or you've got to make the Stokes' theorem argument. One or the other, I need to see for full credit. Okay. How are we doing? Any questions? Is everybody doing all right? Is everybody on board with all this diagnosis stuff we're doing? Okay. All right. Let's see here. Let me choose our last example here carefully. We only have 3 minutes left. That's a good one. Okay, let's do that one. We have one here. This is a Green's theorem problem. Okay, right. Okay, let me be real quick. We are short on time here, and so I'm going to do 2 more examples in the next 3 minutes. I'm going to be really fast. Computing a line integral in R3. Curve given to us. There's the curve. Okay. You take the curl. You don't get 0. Fundamental theorem is off the table. Don't even think about doing the fundamental theorem of line integrals. There is no anti-gradient. Okay. So the option here is to rewrite this line integral we've been asked about, to rewrite it as a flux integral, specifically flux through that surface of the curl. And hey, good news, we just computed the curl. So you could rewrite this line integral as a flux of curl. I would point out, though, that in this example, if you want to compute a flux of that curl, notice the dot product isn't 0, right? The normal vector is 1, 1, 1. This dot product is -3. You're not going to get sort of the geometric good fortune, and we've changed a line integral calculation into a flux calculation. Now, which would you rather? Would you rather parameterize a curve and compute a line integral, or would you rather parameterize a surface? And I'm going to say I'd rather parameterize the curve and do the line integral as opposed to a surface and doing the flux integral. For your consideration. Right? So this is, I think, an example where really, honestly, the best thing is just to take this as a Chapter 5 problem. I think that's the best solution here. If you really want to do it with flux, you can. But another way to say this, just because one of our boundary theorems will allow us to transform the question doesn't mean it's actually going to be useful. Right? So consider the possibility that maybe the original statement of the problem is, it's just a chapter 5 thing, and just do it that way. Okay. The other question I want to get to super quick is this kind of a problem. Again, you'll remember this kind of a surface, and this time what we have is the vector field is given, and I'm also given the same vector field in a different form. I'm told that the vector field is what I have there, but it's also given to be the curl of another vector field. And this tells you a couple of really good things. For one thing, this is your anti-curl. Right? Normally we can't find anti-curls. We don't know how to find anti-curls. Here it's given. Right now I didn't say with big, flashing lights, here's your anti-curl. Right? But suitably interpreted, it's quite clear that that's what this is. This is the thing whose curl is our vector field, so that's the anti-curl. So Stokes' curl theorem is a good way to solve this problem. And it turns out to be a really good way to solve this problem because easy argument, the dot product is 0, as it turns out. But I will also point out another thing that you can get from this, from the same thing, from the fact that this is a curl. Because it's a curl, it follows immediately that the divergence of this vector field is 0. We're taking the divergence of the curl of something, that's definitely 0. This means that we have surface independence. So another very good way to do this problem, just cite surface independence and say, well, look, this surface that I was given, this elliptical paraboloid, I don't like that surface. I'm going to pick this other surface. It's got the same boundary curve. Think about your orientations, like an example we did last time. Now, with this new surface, you've got an alternative flux. And again, you get a dot product that's always equal to 0. And so the surface independent solution is also really good. Okay, so that's the diagnosis on this one. There are a few more examples that you'll notice we skipped over. There's a bazillion examples in this section. I think it's a good idea to read those as well. I encourage you to do that. But we're now done with Chapter 6. We'll finish Chapter 4 tomorrow. And see y'all later. The semester's wrapping up here.